Boom. Hello and welcome back to Calculus 1, 2.6 continuity. Another aspect of functions to be considered. We have continuous and discontinuous functions. Now, a lot of people like to define a continuous function as one that you can draw in one stroke. Okay, fine. But that's not the end of the story, because there are functions which are continuous, but you have to draw them in pieces. So the way they're defined, you actually have to draw a little piece, then stop, then go somewhere else, draw a little piece, and then stop, and then go back and continue drawing on the first piece. Now, these types of functions are studied in advanced calculus. They exist. But then again, in the most basic idea, if you have a line that has no asymptotes, or no vertical asymptotes, no open circles, and no jumps, technically you have a continuous function. So f of x could be represented as a continuous function like this. So I'll just put here, say, continuous. And then over here I'm going to draw a jump. I'm going to draw open circle, and I will say not continuous. So visually it should be very easy to spot continuous versus non-continuous. But we would also like to have mathematical definition for this to try and see what is what mathematical definitions and theorems would help us to determine if something is continuous and not continuous without looking at graphs. Sometimes continuity is in equations is important. Here's why. We talked about vertical asymptotes, right? So if you have a vertical asymptote, like in this case 1 over x, if you have a vertical asymptote, these ends where the vertical asymptotes are trying to go to infinity. Now, you know, mathematically you are okay, it's okay to say, yeah, so what? It's easy to write infinity, just as number 8. Same effort to write both, right? You would also say same line. So, you know, from math standpoint, yeah, it is, who cares? But from application standpoint, this is extremely important. I will give you an example of that you might be familiar with the outlets and short-circuiting the outlet. Did anyone manage to short-circuit outlet ever? And what happened? What happened when you shorted the outlet?
The breaker flips?
Yeah, but what happened at the outlet? The breaker did flip, sure.
Oh.
That was a little explosion, right? Now, why do we have explosion? What is explosion? It's fire. And what is fire? So you can go and backtrack everything to build up of heat. Now, if you are considering formulas from physics, which are well known, and one of those is Ohm's law. Ohm's law says that the current is equal to voltage divided by resistance. And in your outlet, let's say you have 110 volts, you have more than that, but that's fine, divided by the resistance. Now, anything that you plug in has resistance in it, and generally, if your device like your cell phone chargers are 1 amp or 2 amps or so on. So it shouldn't take a lot of mental energy for you to figure out that if you want to have a 2 amp output on the on your charger, that your ohms on the charger should be 50 ohms, 55 ohms, because 110 divided by 55 is 2. So you have 110 ohms, right, for, let's say, the light bulb and whatever. So, you know, this is not exact because AC and DC don't work the same way, but this is just hinting certain things. So now, what I have here is the notion that this R needs to have some kind of a value. Remember, you can't divide by 0. Right? Well, when you short the circuit, R goes to 0. Now, if you have the equation 110 divided by R, and this R wants to go to 0, where is I gonna go? Really? It's going to infinity. So I equals V over R, and we have R goes to 0, I will try to go to infinity. And there is another formula in physics that says that the current is proportional to temperature. So as I goes to infinity, the temperature tries to go to infinity, and there's your explosion. Right? So now you see that continuity, vertical asymptotes, and all of these things are actually related to the stuff you want to build. This curve that you're looking at could be the energy stored in a battery. And then if these things are overlooked in the design, the energy stored tries to go to infinity, and what happens with the battery? Exactly. So there is a circuit that measures the amount of charge stored, because you are actually converting chemical energy of the battery. And then when it's enough, when it's a full charge, it disconnects the charger, so it doesn't go beyond that point in terms of, again, trying to stuff infinite energy into the battery. So these designs are important. Now you can go and translate this into planes and cars and machines that make other stuff, food and stuff, doesn't matter, right? So all of this stuff is relevant, but the relevance of these things you have to learn in courses that are applied courses, where they are just going to say, oh, you remember when you did in math, blah, blah, blah? Now we're going to use it to compute so and so. So you have to learn math first, and then you learn physics, and then you go and you finally go do engineering to build stuff. So now, talking about continuity, I do not want to have vertical asymptotes, because continuous charging of a battery or a continuous path of you driving from home to RV or me driving from home to RV, those need to be continuous functions for our desired outcome. Now, certain things in design want to have discontinuities and interruptions, like servo motors, for instance. That motor needs to spin, and then it needs to stop, and then it's going to get a signal to spin again. So it's not a continuous movement. It spins a little bit, stops, spins the other way maybe, stops. So, you know, for servo motors, it's a welcome behavior or needed behavior. So we are going to now take a look at the definition of the continuity. And the way the continuity works in mathematics is you define the continuity at a single point first, and then you define the continuity, the global continuity, as collection of all individual continuities. So to start the whole story, we take a look at the continuity at the point. And the continuity at the point is going to be, so function f of x is continuous at x equals a if, number one, f of a exists. Well, that should be common sense because the point that you're looking at needs to exist, first of all. And then the limit at that point, so x goes to a, needs to exist. That means that you have to have some path of getting to that point which exists. So that's the limit exists. And then 3, these two guys have to be the same. So limit of f of x needs to be equal to f of a. So this is the big pink box. That's our definition for the continuity at the point. And now I'm just going to draw a graph and quickly pick a point and look at so if I want to check continuity at point A, I better have that point A because that's where I want to go. So you better have a destination. Right? I hope you're not going to school just because. You hopefully have a goal. You want to be a mechanical engineer. You want to be something. So now, that's that part that the point exists in space. And then, remember, continuity. You can't talk about single point. That would be ridiculous, right? At this point, when you woke up this morning, you were at a different point, not here, right? So there has to be some other point somewhere from which you are going to travel to the point where you want to be. That's the second line. The second line says that you have to have the limit exist, which means that, right, the Romeo and Juliet deal, or just one of them, has to be there. So you have to have some line. You can't just have a single point in space and call it continuous. It's not. It's just a single point in space and there's no continuity there. It's just a location. Continuity implies you going along some path. So first one is just the black point. The second one is that you have to be approaching that point walking on a line from left or right, or both. It's okay. And then finally, the third requirement is that those two have to be the same. So the limit and the point of interest have to be the same. Now, the next part in red, if any of the three rules fail, f of x is discontinuous at x equals a. And that is the discontinuity part. Now we can think, concept-wise. I'm going to draw 3 scenarios and we're going to explore this now. So here is one scenario. Oh, this is going to start disappearing. I can sense. I think actually computer senses my excitement to talk about something and then it just starts messing it up. Maybe I should switch to PowerPoint. With the lights off, obviously. For 5 hours. And then everyone goes home. Deal? It's easier for everyone. Great. These are completely arbitrary lines. It's important to have the feature of a jump, feature of the open hole, and the feature of the open hole with the point being somewhere else. Let's all just visually agree this fast that all three are discontinuous. Fair? That should be instantly clear. Before I start talking, I'll shut it off. See?
I can see it. Okay. Come on. There we go. Good. It's alright.
It shouldn't disappear now. Watch it proves me wrong, you delete the whole lecture. So, all right. Looking at our three rules. I'm going to actually write those rules on the board so that we can discuss as a class and figure out which rule is violated on these pictures. So number one, f of a must exist. Number two, limit of f of x as x goes to a needs to exist. And rule number three is that the limit of f of x must be f of a. Right? Great. Which rule out of three is broken on the first graph? Very good. Rule number two. Function value exists. That's that black dot. All right? So, rule number one, pass. Because f of a is right where the black dot is. So we do have rule number one, pass. Rule number two, fail. Limit does not exist, right? So rule number two, fail. You're not even going to check number three because clearly, right, you can't say exist equal does not exist. So as soon as you find the one that is broken, check out right there. How about the next one? Rule one is out. There's no need to go past that. Yeah, rule two is okay, but then again you can't do rule three because rule one was dead. And the last one, by process of elimination, right? First rule holds, second rule holds, and the third rule is out. Because your function value is where the black dot is, and your limit value is where the open circle is, and they're clearly not the same value to satisfy the third rule. So this is mathematical explanation of discontinuities. And there are further divisions later on in calculus, you know, with removable and non-removable discontinuities. For instance, non-removable, non-removable, removable, because you can plug this in, right? It's like when the bridge breaks, this is what you do, right? You plug it, and you make a discontinuous bridge into a continuous bridge, right? If you are one of those people who walk with a stick between two buildings, right? Well, that's discontinuous path until you stretch a little piece of string, and then you go, wee, right? And it becomes continuous. Can't really make this continuous, right? Or this, because there is nothing to plug it in, right? So this one is like you can push it. So there will be further divisions down the line in terms of continuous and discontinuous. But for now, continuity at the point is when all three rules pass. If any of the rules fail, you check out at that point, and the whole thing is, you say, function is not continuous at the point. Now, I want you to be very careful with the statement, because the next definition says global continuity. If the function is continuous at all of its points, it's globally continuous. Ready? So if f of x is continuous at all of its points, then f of x is globally continuous. Now, you have to be a little bit careful. The functions we deal with in Calculus 1 are all piecewise continuous. But they're not all globally continuous. Remember how I said on day 1 that every function has an inverse, but not every inverse is a function? So we have a horizontal line test for that. Well, all of these functions are piecewise continuous, the ones that you see, because this piece over here is perfectly continuous. It's continuous everywhere, and the other part is also perfectly continuous on that interval. The only point of this continuity is here. So, is the function globally continuous? No. It's discontinuous at a. This would be your a, right? For f of a, limit x goes to a. So function is globally discontinuous at a. But function is piecewise continuous. Negative infinity to a and a to positive infinity. So we have two continuous pieces, and then unfortunately globally is discontinuous. Now I want you to stare at 1 over x function. So you have 1 over x here, and you see that the function is definitely globally discontinuous at x equal to 0, because vertical asymptote. But then you have two continuous pieces, therefore piecewise continuous, right, in those areas. So those are just some little... Oh, it killed this as well. Great. So I guess restart. Yeah, it does this every time. It seems that this software is permanently broken. Yeah. Well, definition is there, limit is there, is there, is there. Okay, now these things are gone, obviously. Let's see. Is he going to save it? Yeah, I'm going to call Microsoft. This is gone far enough. Great. So now we have the definition for global continuity. Now note it says all points. How many points are there to, let's say, e to the x?
What?
How many points are there to create a graph of e to the x? And you see, to do this, you actually have to compute them all, right? Check them all. A little bit counterproductive, would you say? So this is why you have to learn the theorem. And the theorem states, following functions are globally continuous. Number 1, all polynomials. Pick any polynomial you can master. It's going to be continuous. 2. Exponential function. 3. Logarithmic function. 4. Radical function, as in nth root of x. Okay? Five, sine x. 6, cosine x. 7, inverse tangent of x. These are functions that we actually need, and we use them all the time. So you have to know that these functions are continuous. Otherwise, you're doomed. So all of these functions are globally continuous at all time. You don't see rational functions clearly because they have denominator equal to 0, creates the vertical asymptote, and discontinuous right away. So you don't have... Now, not all, guys, not all rational functions are going to be discontinuous by default. What happens if your denominator is x squared plus 1? Right? Does that have real zeros? No, it doesn't. Will it have vertical asymptotes? No. Right? So you have to be careful with certain problems. But the theorem deals with those that are globally continuous all the time. So whatever you put for exponential function, 10 to the x, e to the x, whatever you master, it's always going to be continuous. Log base 2, log base 10, log base e, which is ln, all of those globally continuous. Square root of x, fifth root of x, 10th root of x, all globally continuous. Sine, cosine, obviously. Tangent, no. But inverse tangent, yes. If you remember the graph for inverse tangent, it goes like this, forever and forever. That's going to be globally continuous. It's always going to approach pi over 2 and negative pi over 2 as horizontal asymptotes. So these are your globally continuous functions, and you need to remember these because Calc 2. This is where I jump into Calc 2, and then I jump into, let's say, oh, I'm already there. Divergence test, no. Aha, there we go. Integral test. The integral test for series states that one of the rules for us to deal with is that function has to be continuous. Yeah, go ahead, learn it only for the test. See what happens in Calc 2. Hell breaks loose on day 1. So, function has to be continuous. This is just one of the 15 places where I could poke that, where continuity is required. So now, when you have this as a precursor to do the problem, step number 3 to solve a problem is to prove that the function that you're looking at is continuous so that you can use the theorem of the integral test to do whatever Calc 2 wants you to do. So it says x squared is a polynomial, therefore continuous. 1 is a constant, which also belongs in that polynomial thingy, is also continuous. These two statements here came from where? They came from this. Number 1 in blue. All polynomials are continuous. What is the definition for a polynomial? a0 plus a1x plus a2x squared plus a3x cubed, going on forever. And then you have to have the highest exponent. Here's your number 1. When you say function y equals 1, That's just ignoring everything else, keeping the first term only. If you have x squared, y equal x squared, well, that's this puppy here, with this being 0 and this being 0. They're all polynomials. So you are learning now that polynomials are globally continuous everywhere. And then, when you need that, you just pull that theorem from the hat. So Calc 2, Calc 3 differential equations, and so on. You're going to have, I don't know, 15, 20 different concepts going forward, which will ask you to check for continuity. So that's the first theorem. The second theorem immediately follows, which says combinations and compositions of continuous functions are continuous. Combinations and compositions of continuous functions are continuous. What falls under this category? Well, your good old friend f plus g, f minus g, I don't need 1, 2, 3, f times g, f divided by g, provided that g can't be 0, f squared, or f to the n, and then composition, f composed with g, which is f of g of x, or g composed with f, which is g of f of x. Hop over here, back to Calculus 2. First definition, quotient of two continuous functions is continuous if the denominator is not 0. Right? Wasn't that the fourth thing on your list, the purple list I had? So this sentence is that's the fourth rule on the purple list. Since 0 is not in the necessary one, the function is continuous on 1 to infinity. There you go. So this is the way some of the problems in calculus are solved. You write a few sentence paragraph, simply recalling the theorems which you had before. Again, this is me jumping into Calc. We're going to do some of these in Calc 1 as well, but the fastest way, easiest for me to do is to just jump into Calc 2. Whew. Look at the beautiful function. 1 divided by x ln squared x. Not a problem. 1 continuous, x continuous, ln x continuous. Combination of x squared and ln x when you do function composition, since both of those are continuous, is continuous. Division of these is continuous because x couldn't be 0 or 1. The whole thing is continuous. It's the argument. So that's what you have to look forward going to Calc 2, using the theorems from Calc 1. Now we're going back to our lecture and fill in the blanks again. I really don't know. Okay, looks like everything is there. Good. So now, let's have an essay contest over here in the classroom, right? Prove that 3x divided by e to the x minus x squared plus x squared is continuous on 0 to infinity. 0 is not included in the set because I have parentheses. So prove that. Try to write those sentences. You've seen the example in Calc 2, right? Each individual function belongs to the blue theorem and then combination. Let's see what you can master, and then we'll work on it together. You're the best shot. Let's take a look at this together. So I'm going to say 3x e to the x and x squared are all globally continuous, and that is going to be by the blue theorem. And then I just need to show that denominator cannot be 0. So I'll just write, since e to the x plus x squared is not 0, and is never 0, because you can't make it 0. Even if you plug in 0, you get e to the 0 plus 0, which is 1. and you are only on the right, so you can just say, since e to the x on 0 to infinity, we have 3x over e to the x plus x squared to be continuous on 0 to infinity. And that's it. I hope you're not disappointed, but the logic is always show that each individual piece is continuous by the blue theorem, and then hit it with the purple theorem that the combinations are all continuous, as long as, if you have division, as long as division is never 0. And you're done, right? Clearly, it's not going to hold if I involve tangent. Tangent has infinitely many discontinuities. So you can't do this if one of the 3 functions, or whatever amount of functions you have, is discontinuous. Clearly, the whole argument fails. So each individual one needs to be continuous. Like in our case, we have 2 polynomials and exponential. They're all cool. We have the addition. Addition is continuous. And then we have the issue one, which is division. As soon as we show that the denominator cannot be 0, and it can't, because there is no value that you can plug in from the interval we have, to get that 0, we're good to go. Now I would like to take a look at some of the problems from the homework. Oh, this is terrible, by the way, what the book did. Do not. This is terrible. The following functions are continuous at all points of that domain's tangent. We know it's a vertical asymptote pi over 2. Right? They can say on their restricted domains, fine. You restrict the domain of tangent from negative pi over 2 to pi over 2. Sure, we talk about continuity. But it's not the global continuity. So these 4, nope. And these guys also, nope, apart from restricted domains again. So, yeah, I'm not happy. We'll go back to intermediate value theorem, and then that's it. Just want to pick up some problems for you guys to enjoy. So let's see. Is the function continuous? F of x equals x squared minus 1 over x minus 1 for all values if x is not 1, and it's 3 if x is 1. It's a piecewise function. Clearly, where could it be a problem here? At what value? At what value would? 1. Thank you. All right, go on. You have the 3 rules. Rule number 1, rule number 2, rule number 3. Does it pass all 3? You have 19 seconds. Because the theorem, special relativity time flows differently around large objects.
More space-time?
Sometimes when you manage to show up and in your perspective it's 9:15 and I'm at 8:30. It did happen. Actually, I showed up at 9:20 2 years ago, I think, Saturday class. For whatever reason, I thought that the class starts at 9 instead of at 8:30, and I was still 20 minutes late. So I showed up 15 minutes. Everyone was in class, obviously doing labs and stuff, no one laughed. But you don't want to lose a Saturday class. It's the equivalent of the whole week.
Very fun without you.
See? Plus that. I mean, come on. People drive 2 hours for that privilege. Anyway. So let's take a look at this. Rule number 1 is, what's f of 1? Well, f of 1 is 3. That's the second line. If x is equal to 1, y value is 3. I'll circle it one more time, everyone. If x is equal to 1, y value is 3. Perfect. Rule number 1, pass. Rule number 2, does the limit x approaches 1 exist of x squared minus 1 over x minus 1? Yes? Okay, let's see. Limit x minus 1, x plus 1, we have to factor, right? This dies, and the limit is x goes to 1. So we have 1 plus 1 is 2. Pass. Pass rule number 1. Pass rule number 2. Rule number 3. 3 is equal to 2. Not continuous at x equals to 1. Could be continuous everywhere else. It clearly failed rule 3, so I'm actually going to use 2 green check marks. Boom, boom, and then the red one. Not continuous at x equals to 1 because it failed the rule. Another one? Yes, no, who cares? Yes? Yeah, that's the spirit, see? You love this stuff, right? Another problem from your textbook. This is, let's say, 18. Since you love those piecewise function, it's another one of those. So we have x squared minus 4x plus 3 divided by x minus 3. And then you have 2. The first one is if x is different than 3. And this one is if x is 3. Now, just by looking at the top function, continuity issue could be at 3. That should be clear. Where do you detect that issue could be at 3? Do you detect it here or here? Where do you detect? Where to check the continuity? Again, you have 2 possible locations to detect where you should look for continuity piece. So you think is this one or this one? Left or right? Left. Because that one can make a vertical asymptote. So this you can put whatever. I can put 5 and 5, you'll still be looking at 3. Number 1, f of 3 is 2. Thank you. Pass. Number 2, limit x goes to 3 of x squared minus 4x plus 3 divided by x minus 3. Is there a nice way to factor this? What should I have? So what do I get? 2. All right, limit exists. Pass. How about 3? Ooh. All pass. In this case, problem 18 worked out to be continuous. By the way, it's okay to be happy and excited about math. It gets you to SpaceX and other cool places. The last concept that we are going to talk about is intermediate value theorem. This concept is featured on your lab. It's one of the concepts which would utilize continuity, obviously, but it has like this hidden meaning, hidden value, which is really cool. So, intermediate value theorem. We can play music louder than they. Right?
Just 2.7 now?
Nope, still 2.6 and then 15 minutes for 2.7. Then you guys can meet other people in the classroom. I know some of you are already done with the lab 1, but probably majority didn't even look at it yet. So I don't think you have anything meaningful to discuss. All right, so the theorem, maybe put it purple. So let f be continuous on closed interval a, b, and L a number, and L is a number strictly between f of a and f of b. There exists at least one number c in AB satisfying f of c is L. Yay, words, right? How about yay, a picture now? So we have a function f of x before I go too far. I actually don't know if this helps at all, because I did have to write some stuff after I restarted the software. Just I want to believe. How about that? All right. Seems healthy. So I have this, and now what I'm going to do is I'm going to pick A and B, and then they will provide f of A and f of B. So what it says is that there is a number L that is strictly in between f of A and f of B. So you pick somewhere, let's say here, you pick L. There has to be a C that made that L. And that's a C. It doesn't have to be in the middle. Sorry, I drew it in the middle. So that L is actually f of c. Intermediate value theorem. So you have this a and a b on sides, and then if there is a number that you can locate, right, if the function is continuous, if there is a number that you can locate between f of a and f of b, there has to be a c between a or b that made that L. Does this make sense visually? Okay, I'll go over there. So there are f of a and f of b which are produced by a and b. And if you pick any number L between these two guys, there has to be a c that made that L. Made that L, produced that L, whatever. It doesn't sound like, right? Much. But the devil is in the details. You see, everything that we have as a species that we created so far, including the launch, is product of our equations, right? Which need to be solved. And a solution of the equation can always be reduced down to equation equals 0. Meaning, does it have x-intercept? And all of a sudden, we don't use this, but the principle is the one that solves equations. And if you have solution to equation, you can have equation, you can have models, you can have stuff to build. The essence of everything right there, right? In terms of math and building up, right? So now, take a look at this notion here. We are not going to use this. We have calculators and other algebraic methods to do such stuff. But observe function f of x, and you say f of x equal to 0. Well, f of x equals to 0 is here. So you are looking for this value. What is the value c? So that f of x is equal to 0. This is what it means to solve an equation. That equation is equal to 0. You are looking for x-intercept. And the solution of that equation right, is the x-intercept on the graph. Now look at the coolest thing in a galaxy. Maybe, I don't know. You pick value a, which gives you f of a, and you see that f of a is smaller than 0 because it's below x-axis. It's a negative y value. And you pick b randomly, and you see that f of b is larger than 0. And then you can keep picking numbers in between, making this interval smaller and smaller and smaller and smaller. And as long as one of them is negative and one of them is positive, you are guaranteed to have a solution for the equation between those two values. Clearly, if I pick a and b on the same side, they're both positive, and C solution is no longer in between. See that? Visually. So you can actually use this to calculate solution to any equation without knowing how to algebraically solve equation, without knowing the graph or anything like that. You make a guess, and then you use that guess to compute. Let's try, how about x squared minus 3 equals 0? Well, I mean, x squared equals 3, that's the equation, which you transform into x squared minus 3 equals 0. Now, do we all quickly agree that the answers are negative root 3 and positive root 3, so we know what they are, right? But let's say we don't, right? And you want to figure out the decimal answer to this. And what we are going to do? Well, you can say, I hope there is an answer between 0 and 5. Hope there is a solution in 0 to 5. Let's check. What's f of 0? F of 0 is 0 squared minus 3, which is negative 3. And f of 5 is 5 squared minus 3, which is 22. Happy. Why are we happy? We're happy because this one is less than 0, this one is larger than 0, and that guarantees that the 0 is in between. Because you see negative 3 and 22, right? Wow, nice. Okay, fine. Let's make this smaller. So you can go with 1 and 4, but don't. Change one of the sides. So, I don't know, let's cut it in half. Or let's go 0 to 3. Try now 0 to 3. Now clearly f of 0 you already have. That's negative 3, which is less than 0. You have to compute f of 3. F of 3 is 3 squared minus 3, which is 9 minus 3 is 6, larger than 0. Yes! You see that the interval is smaller. You are closer to your answer. You still know that you're on a good track because one endpoint gives you above and one gives you below x-axis. All right, so what should we try now? Well, let's go 0 to 2. Maybe we can cut it even more. Try 0 to 2. Okay, so here it is. F of 0 is still negative 3, which is less than 0. And f of 2 is going to be 2 squared minus 3. That's 4 minus 3, it's 1, bigger than 0. Ha! Okay. My interval now is 0 to 2. It's more than half smaller than when we started. And I'm getting better at this. All right, fine. Let me try 0 to 1. I already know f of 0 is -3, less than 0. And I'm going to try f of 1 now, which is 1 squared minus 3, and that's -2, also less than 0. Solution is not in this interval because both of these are less than 0. Okay, so if the solution is from 0 to 2, and it's not in 0 to 1, where is it? It's 1 to 2, right? So now we immediately fix this and say, okay, recourse, right? We have this. Great. All right. So now we have a new interval to worry about. I don't need to compute it because it's clear that we are still on that interval, right? Because 0 to 2 already worked, and then 0 to 1 failed, so 1 to 2 must contain that root that we are looking for. I don't like that. Don't you twitch on me. All right, now what I'm going to do is I'm going to cut this interval in half, keeping either 1 or 2, doesn't matter. So what should we pick? 1.5 to 2 or 1 to 1.5? Just pick, it doesn't matter what you pick. Yeah, because guys, you will always have 2 buckets. And the solution is in one or the other, right? Because you already know that there is a solution in 1, 2, so it doesn't matter what you pick. Pick one randomly, and we happen to know the solution. So I know the solution up to whatever amount of decimals. So I can always keep picking the right one. It doesn't matter what you pick. Pick one. Which one?
1.5. 1.5.
To 2 or 1 to 1? 2. To 2. Okay, so you want to try 1.5 to 2. Fair. What's f of 1.5? It's 1.5 squared minus 3. And that's going to be 2.25 minus 3. That's less than 0. I don't care how much it is. It's less than 0. It's obviously negative 0.75, but who cares? And we already know from our old calculation that f of 2 is 1, which is larger than 0. Happy, right? Because it passed. It passed. 1 is less, 1 is more. Great. Cut that smaller. Oh, by the way, didn't we already agree that the solution is starting at x equals 1 point something? You see that all of the numbers that remain, and we know 2 is not solution because it didn't give us 0, it gave us 1. So we already know that the solution starts with 1 point, and then there will be decimals here. That's cool. All right, what numbers should I test now? Just give me anything, it doesn't matter. Keep one of the end numbers and change the other one to whatever you want.
1.8, 1.5.
You mean the other way around. So try 1.5 to 1.8. Okay, well, we already know that f 1.5 is less than 0 from the upper calculation. And now I have to go with f of 1.8. 1.8 squared minus 3. What is that? So 3.24 minus 3, 0.24, larger than 0, yay. Great. Pick more. What should we try now? Come on.
1.75, 1.8.
Why you're doing 2? That will be... We'll just do the 1-digit numbers now until we find the first decimal. 1.7 to 1.8. 1.7 to 1.8? Okay, we can do 1.7 to 1.8.
How far did you go?
I'm sorry?
How far did you go?
Oh, you decide what decimal precision you want. We are still looking for the first decimal. So if this works, then the first decimal is definitely 7, because all of the numbers are between 1.7 and 1.8. So if this works out, the solution is 1.7, and then we're going to start chasing the second decimal, and then the third, and then the fourth, and whatever precision you want. You can actually, any computer science here? Go on, write a software for this. It's a loop. It's just if statements. If true, keep cutting. If not true, go back and use the other thing. It should take you about an hour to write this code. I mean, everyone should be writing the code, but then that's your jobs are in the future. What else is there? Right? There's nothing else left. Just have to program AI and robots to build other things. And nurses. The rest is all irrelevant and gone. So now we try this. F of 1.7 is going to be 1.7 squared, which is 2.89 minus 3. That's negative. And we know that f of 1.8 is positive. Oh yeah, there we go. So now we already are building our solution as 1.7. So at least know that much, 1.7. So now that you have this, let's go and try 1.7 to 1.75. And you will see that f of 1.7 is less than 0, f of 1.75 will be larger than 0, so that was the good interval. And then you can test 1.73 to 1.75, and you will see that that also works. And then you try 1.73 to 1.74, and that works, which will immediately mean that your solution now is x.1.73 already. Then you go to the next digit and the next digit and the next digit. So you keep making the interval smaller and smaller and smaller, and as long as one is above and one is below, the solution for the function is in between the two. So you have one of these or two of these problems on your lab to, go on a calculator and spend some time. Obviously, time consuming for the test is all that stuff. We don't use it, right? You plug in Mathematica, solve, and you put the equation and it gives you the answer. But the interesting thing is that you can use this method to whatever kind of complicated equation if you're willing to sit and punch numbers. And it's a really interesting mathematical way to do it, but it's also a really boring and tedious mathematical way to solve every equation out there. And